Hello guys, I am Kirti. Today we will discuss about chapter number 4, alcohols. Introduction. Alcohol constitute a class of compounds which are regarded as hydroxy derivative of hydrocarbons. They are further classified as mono, di and trihydric alcohol according as the number of hydroxyl group present in their molecule is 1, 2 or 3 respectively. Alcohol contain 4 or more hydroxyl groups are known as polyhydric alcohol. Thus we have methyl alcohol monohydric, glycol dihydric, glycerol trihydric, sorbitol polyhydric. It may point out that di, tri, and polyhydric alcohol always have a OH group attached to different carbon atom. This is because the compound having more than one OH group linked to the same carbon is unstable and at once eliminates the element of water as shown below. Aromatic hydroxy compound fall into two categories. These are aromatic alcohol and phenols. Aromatic alcohol. These are compounds in which hydroxy group is present in the side chain. These may be regarded as alcohols in which OH group is attached to an aryl substituted alkyl radical. An important example of such a compound is benzyl alcohol. Phenol. These are compounds which contain hydroxy group on or a group directly attached to an aromatic ring. For example, phenol is an important example. This property of phenol are markedly different from the properties of alcohols and their chemistry, which will be studied in semester 2nd. Monohydric alcohols. These are alcohols having the general formula ROH, where R is a simple or a substituted alkyl group. Thus we have methyl alcohol, ethyl alcohol, benzyl alcohol. Saturated mono alcohols are known as alkanols, as they are derivative from alkanes by the replacement of hydrogen atom by hydroxy group. Alkanols can be represented by a general formula CnH2n plus 1 OH, where N is the number of carbon atom. Classification. Monohydric alcohol may be further classified as primary, secondary or tertiary alcohol as given below. First, primary alcohol. These are alcohol in which the hydroxy group is attached to a primary carbon. For example, ethyl alcohol, propyl alcohol, benzyl alcohol. It is apparent that the carbon which carried the OH group has at least two carbons attached to it. In other words, primary alcohol has a characteristic group CH2OH present in them. Secondary alcohol. These alcohol contain hydroxy group attached to a secondary carbon atom. For example, isopropyl alcohol, secondary butyl alcohol. In these alcohols, the carbon carry the OH group has only one hydrogen atom attached to it. As such, the characteristic group in which alcohol is attached to CHOH. Tertiary alcohol. These are alcohol in which hydroxy group is attached to a tertiary carbon atom. For example, tertiary butyl alcohol. It is clear that carbon carry the OH group has no hydrogen attached to it. This means that the characteristic group present in these alcohol is COH. Nomenclature of monohydric alcohol. Monohydric alcohol are named by three different systems. First, the common system. According to this system, which is used only for simpler alcohols are named by adding the word alcohol to name of alkyl group present in the molecule. For example, methyl alcohol, ethyl alcohol, and propyl alcohol. Isopropyl alcohol, tertiary butyl alcohol, benzyl alcohol. Second, carbonyl system. According to this system, methyl alcohol is called carbinol, and other alcohol are named as alkyl derivative of a carbinol. For example, carbinol, methyl carbinol, dimethyl carbinol, triphenol carbinol. However, this system is used only rarely. Third, UPAC system. UPAC system. In this system, alcohol are named in accordance with the generally IUPAC rule. The main point involved in nomenclature are summed up below. First, the long carbon chain containing the carbon atom carrying the hydroxyl group is selected as according to the parent hydrocarbon. The alcohol in which as derivative of hydrocarbon we replace the finally E of the name of a hydrocarbon by the suffix OL. Second, the parent chain of a carbon atom is numbered from that end which gives the lowest possible number to carbon carrying the hydroxy group. Third, the name of alcohol is then written as one word by substitution the name of the side chain or substitution along with their position in alphabetically order, followed by the name of parent alcohol. For example, ethanol, butane 1-ol, methyl propane 1-ol, 2-methyl propane 2-ol, phenyl ethane 1-ol. The common and IUPAC name of a few alcohol are given below. CH3OH, common name methyl alcohol, IUPAC name methanol. CH3CH2OH, ethyl alcohol, IUPAC name ethanol. So on. Structural isomerism. Monohydric alcohol exhibits three types of structural isomerism. First, chain isomerism. This type of isomerism is due to the difference in nature of a carbon chain attached to a hydroxyl group. It is exhibited by the alcohol having 4 or more carbon atoms. For example, butane 1-ol, 2-methyl propane 1-ol. Second, position isomerism. It is due to the difference in the position of hydroxyl group in the chain of a carbon atom, butane 1-ol or butane 2-ol. In generally, the total number of isomerism saturated monoalcohol chain as well as position isomerism is 2 to the power n minus 2, where n is the number of carbon atom. Thus, there are 8 isomeric alcohol having molecular formula C5H11OH. Third, functional isomerism. Monohydric alcohol also exhibits functional isomerism, which another class of oxygen derivative, namely ether. Example, ethanol and monomethoxymethane. This problem number 4.1. Write the structural formula and IUPAC name of the following alcohol having molecular formula C5H12O. These are the structural formulas and IUPAC's name of a C5H12O. Method of preparation. Reduction of carbonyl compounds. Alcohol can be easily obtained by the reduction of aldehyde, ketone, carboxylic acid, ester, etc. by a variety of reduction reducing agent as discussed below. First, reducing by aldehyde and ketone. Aldehyde can be reduced to primary alcohol and ketone to secondary alcohol in number of ways as given below. A. Catalytic hydrogenation. Aldehyde and ketone can be easily reduced to primary and secondary alcohol respectively by hydrogenation in the presence of catalysts such as nickel, platinum, that is, aldehyde plus hydrogen in the presence of nickel give primary alcohol. Ketone plus hydrogen in the presence of nickel give secondary alcohol. For example, propanaldehyde plus hydrogen give in the presence of nickel give propyl alcohol. Catalytic hydrogenation of an aldehyde or ketone containing other easily reducible groups such as carbon-carbon double bond, which furnish product in which both the functional groups are attached. For example, cartinol aldehyde in the presence of hydrogen plus hydrogen in the presence of nickel give N-butyl alcohol. Therefore, this method cannot be used if it is derived to carry out the selective reduction of only carbonyl group, keeping the other group intact. B. Reduction with the complex metal hydride. The reduction of aldehyde and ketone to be prepared alcohol is usually carried out in the laboratory with the complex metal hydride as lithium aluminium hydride LiAlH4 and sodium boride NaBH4. Aldehyde and ketone give primary and secondary alcohol in the presence of lithium aluminium hydride and sodium borohydride. Sodium borohydride is easier to handle and can be used either in water or alcohol solution. The reduction product initially formed get hydrolyzed to form alcohol. For example, butanol in the presence of sodium boride in ethanol and second in H3O positive give butane 1-ol. Lithium aluminium anhydride react violently with water and alcohol. It can be used only in aprotic solvent such as dry ether or tetrahydrofuran. The product initially formed is then subjected to hydrolysis to get the alcohol. Butane 2-on in the presence of lithium anhydride and ether plus H3O positive give butane 1-ol. Mechanism. Reaction of aldehyde and ketone by both lithium aluminium hydride and sodium boron hydride occur through the nucleophilic attack of hydride ion on a carbonyl group to form a complex containing an OB or OAl bond. This species has still got 3 metal hydrogen bonds and react further with 3 more molecules of carbonyl compound. The metal alk oxide intermediate thus formed is hydrolyzed to get alcohol as shown below. It may be seen that one molecule of NaBH4 or LiAlH4 reduces 4 molecules of aldehyde or ketone. But lithium aluminium hydride and sodium borohydride are selectively in their reduction action. In the reduction of aldehyde and ketone containing isolated carbon-carbon double bond, only the carbonyl group get reduced by these reagents. For example, hexa 4-in-2-ol in the presence of lithium aluminium hydride or sodium borohydride. Second, H3O positive give hexa 4-in-2-ol. In such compound which contain carbon-carbon double bond in conjugation with carbonyl group, sometimes the double bond may also get reduced along with the carbonyl group. The chance of reduction of both functional groups are more with lithium aluminium hydride than with sodium borohydride. For example, gamma phenol propyl alcohol carbon-carbon double bond is also reduced from cinemal aldehyde. If in the presence of sodium borohydride and H2O positive, carbon-carbon double bond is not reduced. Thus, NaBH4 is less vigorously and more selectively than lithium aluminium hydride. It may be recalled that a reagent which attacks only one functional group and not the other group which is present is known as rheoselective reagent. A very effective rheoselective reagent acting for carbonyl group developed recently is 9BBN, 9-borobicyclone 331-nonane. C. Marivin-Pondorf-Verifile reduction. It is a commonly used reaction for the reduction of a ketone to secondary alcohol. This reaction is carried out by heating the carbonyl group in isopropyl alcohol in the presence of aluminium isopropyl, also known as Marivin-Pondorf-Verifile reagent, and distilled of acetone from the reaction mixture. The other functional group, if any, present in carbonyl compound remain unaffected. Ketone plus isopropyl alcohol in the presence of aluminium isopropoxide give secondary alcohol plus acetone. Distilled of. It is a reversible reaction, but the equilibrium is pushed in forward direction by distilling of acetone as soon as it is formed. Mechanism. Second, reduction of carbonyl acid, carboxylic acid. Primary alcohol can be obtained by the reduction of carboxylic acid by lithium aluminium hydride. Sodium borohydride does not reduce carboxylic acid. In this reaction, the carboxyl part of a carboxylic group is reduced to CH2 group. For example, carboxylic acid in the presence of lithium aluminium hydride and ether give primary alcohol. For example, butyric acid in the presence of lithium aluminium hydride and ether give 1-butane or mechanism. The reduction takes place through the formation of intermediate alkoxide, which yield the alcohol on hydrolysis. This method is generally employed for the preparation of alcohol from acid which are readily available for natural source. Carboxylic acid can also be reduced to primary alcohol by the action of diborane. Third, reduction of esters. Reduction of esters constitute of a convenient method of preparation of alcohol. The reduction is generally carried out by the following method. Bovillatte-Blanc reduction. This method involves the reduction of ester to alcohol by treating with sodium in alcohol. The reaction leads to the formation of mixture of two alcohol, one which is formed from alkoxy group and second which is formed by alkyl group. For example, ethyl propanoate in the presence of sodium and ethyl alcohol give 1-propanol and ethanol. Mechanism. The reaction is believed to take place in a number of steps and involves the transfer of one electron at a time from sodium metal as summed up ahead. B. Reduction with lithium aluminium hydride. Ester can also be reduced with lithium aluminium hydride to yield a mixture of two alcohols, as in case of Bovillatte-Blanc reduction. Ethyl butyrate in the presence of lithium aluminium hydride and ester give 1-butanol and ethanol. Mechanism. The reaction takes place by the addition of hydride ion to a carbonyl part of ester group. This is followed by the elimination of alk oxide ion to yield an aldehyde intermediate which is not isolated. Further reaction of lithium aluminium hydride with aldehyde give primary alcohol. C. Catalytic hydrogenation. On an industrial scale, alcohols are obtained from ester by catalytic hydrogenation in the presence of copper chromide catalyst. For example, ethyl propanate in the presence of hydrogen catalyst copper chromate is used to give 1-propanol and plus ethanol. Fourth, Grignard synthesis. By far the most important method for the preparation of primary, secondary and tertiary alcohol is by the reaction between a Grignard reagent and a carbonyl group such as aldehyde or ketone. The addition product initially formed is decomposition with water, preferably in the presence of acids such as HCl or H2SO4 to get the alcohol. The general reaction may be depicted as follows. Carbonyl group compound plus Grignard reagent in the presence of dry ether give additional product, then we add water to give alcohol. First, if the carbonyl compound is used in the above reaction is formaldehyde, the final product is primary alcohol. Second, when the carbonyl compound used is some aldehyde other than formaldehyde, the final product is secondary alcohol. Third, use of ketone to react with Grignard reagent lead to ultimate formation of a tertiary alcohol. It may be noted that in all these reactions, the number of carbon atom in alcohol obtained is equal to the sum of a carbon atom in aldehyde or ketone and Grignard reagent. Fifth, by the hydrolysis of esters. The hydrolysis of ester with alkyl solution is generally employed for the preparation of alcohol from a naturally occurring ester. Ester plus aqueous NaOH gives sodium salt of acid and alcohol. Hydration of alkenes. Alkenes can be hydrated to form alcohol either through addition of sulfuric acid or by the direct hydrogenation as described below. A. Addition of a sulfuric acid followed by hydrolysis. Alkene react with the cold concentrated H2SO4 to form alkyl hydrogen sulfide. Alkyl hydrogen sulfide are easily hydrolyzed by heating with water to form alcohols. For example, ethylene plus ethyl hydrogen sulfate give ethyl alcohols. In case of unsymmetrical alkene, addition of sulfuric acid takes place according to Markovnikov rule. B. Direct hydrogenation. The more reactive alkene directly adds on water in the presence of acids such as sulfuric acid and phosphoric acid to yield alcohols in accordance with Markovnikov rule. 7. Oxymercutation, demercutation of alkenes. It is a very convenient two-step method for preparing alcohol from alkene. When we treat with mercuric acetate in a water trihydrofuran solution, alkene form organomercurial compound. These mercury compounds are reduced by sodium borohydrate to yield alcohol, that is, alkene plus water plus mercuric acetate in the presence of tetrahydrofuran give organomercurial compound plus carboxylic acid. Then, in the presence of NaBH4 give alcohol plus mercury plus carboxylate ion. In the first step, water and mercury acetate add to a double bond. This is known as oxymercutation. In the second step, sodium borohydrate reduce the mercurial compound and the mercuric acetate group gets replaced by hydrogen. This is known as demercuration. Both the steps take place very rapidly and conveniently at room temperature. The organomercurial compound formed in the first step is not isolated but is reduced in acid by sodium borohydrate to form alkyl in very high yield. Oxymercutation and demercutation is highly reoselective and the alcohol form is in accordance with Markovnikov addition of water to a carbon-carbon double bond. Thus, the overall reaction may be summed up as follows. Example: 2-methyl-but-1-ene in the presence of hydrogen, mercuric acetate and tetrahydrofuran and sodium borohydrate give 2-methyl-2-butanol. In writing this reaction, acetate group is often abbreviated as OAC. 8. Hydroboration oxidation of alkene. When treated with diborane BH3 twice, alkene undergoes hydroboration to form alkyl boranes. The alkyl boranes are readily oxidized by hydrogen peroxide in alkene solution to form alcohols. Thus, the net result of a reaction also is the addition of water to alkene to form alcohols. For example, ethylene plus diborane give ethyl borate and then give diethylboranes, then triethylboranes. When we hydrolyze with H2O2, it gives ethyl alcohol and boric acid. The overall reaction may be presented as ethylene in the presence of diborane and H2O2 give alcohol, ethanol. Hydroboration oxidation is also a reuse-selective reaction and the alcohol obtained in such as if anti-Markovnikov addition of water to alkene has taken place. As such, this method can be used for preparation of alcohol which cannot be prepared by other method of hydration of alkene. For example, propylene in the presence of diborane and H2O2 negative give 1-propanol. It may be noted that due to anti-Markovnikov addition, only primary and secondary alcohol can be prepared by this method. By the hydrolysis of alkyl halide. The hydroxide of alkyl halide with an aqueous solution of a sodium or a potassium hydride or most silver oxide result in the formation of alcohol. Alkyl halide plus aqueous KOH give alcohol and KX. 10th, by the fermentation of a carbohydrate. This method has been used since very easily time for a large-scale preparation of ethyl alcohol. The carbohydrate employed in this process is either sugar, used either in the form of molasses or obtained from such other sources like grapes, beetroot, etc., or some starchy material like potatoes, barley, rice, or maize. This reaction takes place are summarized below. From sugar, C12H22O6 plus water invest into glucose and fructose. Then, in presence of gymase, give ethyl alcohol plus carbon dioxide. From starch, C6H22O5 and twice plus NH2O in the presence of diase give maltose and C12H22O11 plus H2O in the presence of maltase give glucose. Glucose in the presence of gymase give ethyl alcohol plus carbon dioxide. This fermented liquor obtained by the above method is known as wash or contain up to 18% ethyl alcohol. It can be concentrated by fractional distillation. Physical properties of alcohol. Due to the presence of OH group in a molecule, alcohol are polar compounds. Oxygen is more electronegative than carbon or hydrogen, so that the electron of carbon, oxygen as well oxygen hydrogen bond are replaced toward the oxygen atom. Therefore, the oxygen atom carried partially negative charge while both carbon and hydrogen attached to oxygen carry partially positive charge. Moreover, like water, alcohol molecule also has a bent structure so that we may represent alcohol molecule as. Because of a bent structure and molecule nature of carbon, oxygen and oxygen hydrogen bonds, alcohol possesses considerable dipole momentum. The above structural feature of alcohol has a strong influence on the physical and chemical properties of alcohol as discussed below. First, physical state. The lower alcohol or colorless liquid has a distinct alcoholic smell and a burning taste. The higher member are colorless, tasteless, waxy solid. Second, associated state. Hydrogen bond. Since alcohol contains hydrogen attached to strongly electronegative oxygen, extent intermolecular hydrogen bonding exists between alcohol molecules. As such result, alcohol exists in form of associated molecule and not simple monomeric molecule. Third, boiling point. The boiling point of alcohol are much higher than those of hydrocarbons or ethers or of a comparable molecular weight, as is evident from the following example. Ethyl alcohol, molecular weight 46, boiling point 351.5 Kelvin. Dimethyl ether, molecular weight 46, boiling point 249. Propane, molecular weight 44, boiling point 231. The higher boiling point of alcohol can be explained in terms of extensive intermolecular hydrogen bonding in alcohol. Large amount of energy is required to break these hydrogen bonds which hold the alcohol molecule together in the associative state. Therefore, alcohol molecule at much higher temperature than alkane and ether, etc., which do not form intermolecular hydrogen bonding. Almost themselves, the boiling point of isomeric alcohol are ordered primary, secondary, tertiary. This is because out of isomeric alcohol, primary alcohol are most polar and form hydrogen bonding to the maximum extent as compared to secondary and tertiary. With increase in molecular weight, the boiling point increase regularly. Fourth, solubility. The lower alcohol are highly soluble in water with the solubility decrease with increase in molecular weight. The higher solubility of lower alcohol is due to formation of hydrogen bond with alcohol and water molecule. The rapid fall in solubility of a higher alcohol is due to the fact that with increase in molecular size, the non-polar hydrocarbon character of a molecule become more dominating in comparison with the polar OH group. This lead to a decrease in the extent of hydrogen bonding formation with water and therefore the solubility in water decrease. For isomeric alcohol, the solubility increase with increase in branching. This is because of the reason that as the branching increase, the surface area of non-polar hydrogen part decrease. The higher alcohol, it may be not are more soluble in organic solvent. Fifth, density. Generally speaking, the density of alcohol is lesser than that of water, although it increases with increase in molecular weight. Chemical property. The hydroxyl group present in alcohol is a very reactive group and the characteristic reaction of alcohol a reaction of OH group. In general, the reaction of alcohol may be divided into the following three categories. First, reaction involving the cleavage of OH bond, such that ROH. Reaction involving the cleavage of carbon and oxygen bond, ROH. Reaction involving both alkyl and hydroxyl group of alcohol molecule. First, reaction involving the cleavage of OH bond. Generally, order of reactivity of alcohol in this type of reaction is primary, secondary, then tertiary. Explain. In the cleavage of OH bond, oxygen, which is more electronegative than hydrogen, take always both the electron of shared electron pair. Therefore, relatively reactivity of alcohol in the presence of reaction can be explained in terms of electron releasing plus I, inducing effect of alkyl group. As we move from primary to secondary tertiary alcohol, the number of alkyl group attached to carbon carrying the OH group increasing from 1 to 3. Due to this, the electron density around oxygen goes on increasing on moving from primary to secondary then tertiary. The result is that the electron of OH bond cannot be sufficiently drawn toward oxygen and the cleavage of OH bond decrease. Thus, the order of reaction involving the cleavage of OH bond is primary, secondary, then tertiary. It can be easily understood that methyl alcohol, which has only 3 hydrogen attached to a carbon carrying OH group, would be most reactive of all alcohols. First, reaction with metal, acidic nature. Alcohol react with active metal like sodium, potassium, magnesium, and aluminium to liberate hydrogen and form metal alcohols or alkoxides. For example, ethyl alcohol in the presence of sodium gives sodium ethoxide plus hydrogen. The reaction suggests that alcohol are acidic in nature. This is quite understandable since the OH group contains highly electronegative oxygen attached to hydrogen. Naturally, the OH bond is polarized in character, and although the separation of hydrogen adds at positive ion, however, alcohol are very weak acid, even weaker than water. This is because the alkyl group present in alcohol have a electron releasing inducing effect. This case an increased electron density around oxygen. The result is that electrons of OH bond are not sufficiently drawn toward oxygen and the release of proton is rendered difficult. In other words, the plus I effect of alkyl group makes the alcohol weaker than the water. Comparison of strength of 1 degree, 2 degree and 3 degree alcohol. Since the plus I effect would be maximum in tertiary alcohol, which has 3 alkyl group attached to carbon bearing the OH group, and least in a primary alcohol have only one alkyl group attached to carbon of OH bond. The order of acidity of alcohol is decreasing in order primary, secondary and tertiary. It is the evidence that methyl alcohol would be stronger even than ethyl alcohol and other primary alcohol since it has no alkyl group attached to a carbon carrying OH group. Second, reaction with Grignard reagent. Alcohol reacts with Grignard reagent to provide hydrocarbon as shown below. Alcohol plus Grignard reagent give hydrocarbon. It may be noted that alkene formed corresponds to alkyl group to Grignard reagent. Third, reaction with organic acid. Alcohol reacts with organic acid to form ester. This is a slow reversible reaction termed as esterification. It is generally carried out in the presence of concentrated sulfuric acid or hydrogen chloride gas. Acid plus alcohol give ester plus water in the presence of H2SO4. The reaction is reversible in nature, but the equilibrium can be pushed in a forward direction by removing the water from formed continuously. This is done with the help of an apparatus called Dean and Stark separator. If the esterification is carried out in the presence of HCl, it is known as Fischer-Payet esterification. For example, acetic acid plus ethyl alcohol in the presence of acid give ethyl acetate plus water. Mechanism. The reaction of esterification involves the initial propionation of a carbonyl oxygen of a carboxylic acid by the proton releasing by mineral acid. As a result of a carbonyl compound, carbonyl carbon become more positively charged and readily undergoes nucleophilic attack by the oxygen of alcohol. The resulting intermediate is ultimately converted into the ester is depicted below. Isotopic trace studies have confirmed that esterification involves the cleavage of OH bond of alcohol and COH bond of acid as suggested by the above mechanism. For instance, let us consider the esterification reaction of acetic acid and ethyl alcohol has an isotope of oxygen of atomic weight 18 in the hydroxyl group. At the conclusion of esterification reaction, the isotopic oxygen would be found to be present in ester and not in water as shown below. Relative reactivity of alcohol and acid. The relative reactivity of alcohol and acid in the reaction are strongly influenced by steric hindrance caused by the presence of a large group in them. The greater the size of a group near the OH group of alcohol or a COH group of acid, the slower the rate of esterification. For example, the decrease the rate of esterification, some alcohol and acid are methanol, ethanol, propanol, butane, all. For example, जैसे कि मिथेनोइक एसिड, इथेनोइक एसिड, प्रोपेनोइक एसिड, ब्यूटेनोइक एसिड. Fourth, reaction with acid halide or acid anhydride. When alcohol are reacted with an acid hydride or acid anhydride, the hydrogen of OH group is replaced by alkyl group. And once again an ester is formed. The reaction known as acetylation takes place more rapidly than esterification with carboxylic acid themselves. Thus we have acetic chloride plus ethanol give ethyl acetate plus HCl. It may be noted that in the case of polyhydric alcohol, hydrogen of each OH group is replaced by alkyl group to form polyester. For example, 1 mole of grease flour react with 3 mole of a triester. Mechanism. Reaction mechanism may be depicted as follows. Reaction with acid halide or acid anhydride. When alcohol are heated with acid halide or acid anhydride, the hydrogen of OH group is replaced by alkyl group. And once again an ester is formed. This reaction, known as acetylation, takes place more rapidly than esterification with carboxylic acid themselves. Thus we have acetyl chloride plus alcohol give ethyl acetate. It may be noted that in case of a polyhydric alcohol, hydrogen of each OH group is replaced by alkyl group to form polyester. For example, 1 mole of glycerol reacts with 3 mole of acetyl chloride to form a triester. Mechanism. The reaction may be depicted as follows. First, with acid chloride. जैसे कि हम देख सकते हैं जो डबल बॉन्ड का इलेक्ट्रॉन है कार्बन वाला वो तो ऑक्सीजन के ऊपर चला जाएगा और एल्कोहल में OH वाले इलेक्ट्रॉन है वो कार्बन के ऊपर बॉन्ड बना लेंगे। बाद में कार्बन के पास 3 बॉन्ड हो गए तो इस पर पॉजिटिव चार्ज आ गया, पॉजिटिव चार्ज आ गया तो इसको कम करवाने के लिए H पॉजिटिव निकल जाएगा। इससे हमें हमारा क्या बन जाएगा, एस्टर बन जाएगा। फिर हम करेंगे विद एसिड एनहाइड्राइड। एसिड एनहाइड्राइड में भी ऐसे होगा, ऑक्सीजन का डबल बॉन्ड का इलेक्ट्रॉन ऑक्सीजन के ऊपर चला जाएगा, फिर ऑक्सीजन का के लोन पेयर कार्बन के साथ बॉन्ड बना लेंगे, इस पे ऑक्सीजन पे पॉजिटिव चार्ज आ जाएगा, फिर हाइड्रोजन निकल जाएगा। Reaction involving the cleavage of carbon and oxygen bond in alcohols. In these reactions, the bond between carbon of the alkyl group and oxygen of a hydroxyl group get repartured. The order of reactivity of alcohol in this type of reaction is tertiary alcohol, secondary alcohol, then primary alcohol. Explanation. The above order of reactivity can be explained in terms of plus I effect of an alkyl group. As they move from primary to secondary to tertiary alcohol, the number of alkyl group attached to a carbon carrying the OH group increase. Due to this, the electron of the carbon and oxygen bond OH bond are pushed more and more toward oxygen. As a result, the carbon and OH bond become more and more polar and therefore more reactive. In other words, tertiary alcohol would be the most reactive in such reaction, and the reactivity will be lesser and still lesser in case of a secondary and primary alcohol. It is the evidence that methyl alcohol would be least reactive of all alcohol. First, reaction with hydrogen halide. Alcohol reacts with hydrogen halide to form alkyl halide and water. Alcohol plus HX give alkyl halide plus water. Hydrogen bromide and hydrogen iodide react in the same way as shown above in the case of a hydrogen chloride, but without in the presence of dehydrated agent anhydrous ZnCl. 2. If an alcohol is heated with hydrogen iodide in the presence of red phosphorus, it gets reduced to a hydrocarbon. For example, methyl alcohol plus 2HI in the presence of red phosphorus give methane plus water plus I2. The order of reactivity of a halogen acid is HI, then HBr, then HCl, while the order of reactivity of alcohol is tertiary, secondary, primary. Due to its low reactivity, the reaction of hydrogen chloride with primary and secondary alcohols require the use of a catalyst such as anhydrous ZnCl. Lucas reagent. Due to the presence of reactivity of 1 degree, 2 degree, 3 degree alcohol with halogen acid, the reaction of HCl and anhydrous ZnCl2, known as Lucas reagent, is used for distinguish between different classes of alcohol. Tertiary alcohol react with Lucas reagent immediately to produce the cloudiness due to the formation of alkyl chloride. Secondary alcohol react with Lucas reagent less rapidly to produce a cloudiness after 2 or 3 minutes. 3. Primary alcohol react with Lucas reagent only on heating and no cloudiness is produced in the cold. Mechanism. The mechanism of a reaction is believed to be as followed except in case of a methanol and most of a primary alcohol. Alcohol plus HX. Protonated alcohol plus X. Second, protonated alcohol slowly reaction R पॉजिटिव प्लस H2O निकल जाएगा, जिसमें R पॉजिटिव और X नेगेटिव की रिएक्शन होने पर RX बन जाएगा. This is obviously an SN1 mechanism involving a protonated alcohol as the substrate and the halide ion is as nucleophile. This mechanism is supported by the fact that the observed order of relativity reactivity of alcohol is the same as order of stability of a carbocation. The formation of a rearrangement produced in many cases further support the intermediate formation of a carbocation. For example, neopentyl alcohol plus HCl give protonated neopentyl alcohol. Primary carbocation, then rearrangement of first 1 and 2 alkyl shift. Reaction with acid halide or acid anhydride. When alcohols are heated with an acid halide or acid anhydride, the hydrogen of OH group is replaced by alkyl group. And once again an ester is formed. The reaction known as acetylation takes place more rapidly than esterification with carboxylic acid themselves. Thus we have acetyl chloride plus alcohol give ethyl acetate. It may be noted that in case of a polyhydric alcohol, hydrogen of each OH group is replaced by alkyl group to form polyester. For example, 1 mole of glycerol react with 3 mole of acetyl chloride to form triester. Mechanism. The reaction may be depicted as follows. Reaction involving the cleavage of a carbon and oxygen OH bond. In this reaction, the bond between carbon of alkyl group and oxygen of a hydroxy group get ruptured. The order of reactivity of alcohol in this type of reaction is trialcohol, tertiary alcohol, secondary alcohol, then primary alcohol. Explanation. The above order of reactivity can be explained in terms of plus I effect of alkyl group. As we move from primary to secondary to tertiary alcohol, the number of alkyl group attached to a carbon carrying the OH group increases. Due to this, the electron of a carbon and OH group OH bond are pushed more and more toward oxygen. As a result, the carbon and OH group bond become more and more polar and therefore more reactive. In other words, tertiary alcohol would be the most reactive in such reaction and the reactivity will be lesser and still lesser in case of a secondary and primary alcohol. It is also evidence that methyl alcohol would be least reactive of all alcohol. First, reaction with hydrogen halide. Alcohol react with hydrogen halide to form alkyl halide and water. Alcohol plus HX give alkyl halide plus water. For example, ethyl alcohol plus HCl in the presence of anhydrous ZnCl give ethyl chloride plus water. Hydrogen bromide and hydrogen iodide react in the same way as shown above in case of hydrogen chloride but without the presence of dehydrated agent and anhydrous ZnCl2. If an alcohol is heated with hydrogen iodide in the presence of red force, it gets reduced to hydrocarbon. For example, methyl alcohol plus. The order of reactivity of halogen acid is Hi, then HBr, then HCl, while the order of reactivity of alcohol is tertiary, primary, secondary. Due to its low reactivity, the reaction of hydrogen chloride with primary and secondary alcohol require the use of catalysts such as anhydrous ZnCl. 2. Lucas test. Due to the difference in reactivity of 1 degree, 2 degree and 3 degree alcohol with halogen acid, the reaction of HCl and anhydrous ZnCl2 known as Lucas reagent is used for distinguish between different classes of alcohol. First, tertiary alcohol react with Lucas reagent immediately to produce a cloudiness due to a formation of alkyl chloride. Second, secondary alcohol react with Lucas reagent less rapidly to produce a cloudiness after 2 or 3 minutes. Third, primary alcohol react with Lucas reagent only on heating and no cloudiness in produced in cold water. In cold. Mechanism. The mechanism of reaction is believed to be as followed except in case of methanol and most of the primary alcohols. Alcohol plus HX give protonated alcohol or oxynium ion plus X. Second slow step carbocation plus water formed. Then carbocation plus halide give Rx. This is obviously an SN1 mechanism involving a protonated alcohol as the substrate and the halide ion as a nucleophile. The mechanism is supported by the fact that the observed order of a relative reactivity of alcohol is the same as the order of stability of a carbocation. The formation of rearrangement product in many cases further supported the intermediate formation of carbocation. For example, new pentyl alcohol in the presence of HCl give protonated alcohol and therefore water reduce give primary carbocation. Then there is a shift rearrangement of 1 to alkyl shift give more stable tertiary carbocation. Then react with Cl negative give tertiary pentyl chloride. Alternate mechanism. It has been observed that primary alcohol other than neophenyl alcohol do not form rearrangement product. To account for this, an alternate SN2 mechanism which does not involve the formation of a carbocation intermediate has been proposed for methanol and most of the primary alcohol. Thus we have second, reaction with phosphorus halide. Alcohol react with phosphorus halide such that PCl5, PCl3, PBr3, PBI3 to yield corresponding alkyl halide. Alcohol plus PCl5 give alkyl chloride plus POCl3 plus HCl. For example, benzyl alcohol plus PCl5 give benzyl chloride plus POCl3 plus HCl. Ethyl alcohol plus Pi3 give ethyl iodide plus H3PO3. Mechanism. The mechanism of reaction between alcohol and PX3 may be illustrated by considering the reaction between alcohol and PCl3 as given below. In the first step, nucleophile attack of alcohol on PCl take place to form a protonated alkyl dichloride phosphide. In the second step, chloride ion act as nucleophile and displace HOPCl3 to form the phosphate initially formed. HOPCl2 react with more alcohol by repetition of step first and second to form RCl, and HO twice PCl further react with HO twice PCl and alcohol by step first and second give rise to another molecule of RCl and OH thrice P or H3PO3 thus react ultimately lead to conversion of 3 mole of alcohol into alkyl chloride by 1 mole of PCl3. The mechanism has been proposed for reaction between alcohol and PCl5. Third, reaction with thionyl chloride. Alcohol react with thionyl chloride preferably in the presence of base such as tertiary amine to form alkyl chloride. Alcohol plus thionyl chloride give alkyl chloride plus SO2 plus HCl. For example, ethyl alcohol plus SOCl2 give ethyl chloride plus SO2 plus HCl. The base promote the reaction by reacting with HCl, that is, tertiary amine plus HCl give alkyl amine plus Cl negative. Mechanism. The reaction is believed to take place as follows. Reaction involving both alkyl and hydroxy group. First, acidic dehydration when alcohol are reacted with sulfuric acid, phosphoric acid or boric acid, or when their vapor are passed over heating aluminium oxide which act as Lewis acid. Alcohol get dehydrated to form alkene. For example, alcohol in the presence of H2SO4 temperature 433 to 443 Kelvin give ethylene. N-butyl alcohol in the presence of H2SO4 give 2 butene plus 1 butene plus water. The reaction between alcohol and sulfuric acid is very sensitive to condition of a reaction, furnishing different produce under different conditions. For example, when ethyl alcohol is treated with sulfuric acid, ethylene hydrogen sulfate is obtained at 383 Kelvin. Ethanol plus H2SO4 at 383 Kelvin give CH2H5HSO4 plus H2O, ethyl hydrogen sulfate plus water. Ethyl hydrogen sulfate so produced when subjected to specific condition give the following three different products. On distillation under reduced pressure, ethyl hydrogen sulfate form diethyl sulfate. B. When heated to 413 Kelvin in the presence of excess of alcohol, ethyl hydrogen sulfate react further to give ether. C. On other hand, if we heat it to 433 to 443 Kelvin in the presence of excess of sulfuric acid, ethyl hydrogen sulfate change into ethylene. Mechanism of dehydration. The mechanism of dehydration of alcohol involves the formation of carbocation as an intermediate. The reaction is believed to take place in three steps. In the first step, alcohol combines with hydrogen ion to form protonated alcohol or oxenium ion. The step second involves the dissociation of oxenium ion and formation of a carbocation. Finally, the carbocation loses a hydrogen ion to a fresh molecule of alcohol to yield the alkene. The various steps are illustrated ahead with the help of ethyl alcohol. All the three steps shown above involve reversible equilibria. However, the resulting alkene is much more volatile than starting alcohol and is easily driven out from the reaction mixture. This shifts the equilibrium in step 3 toward the right. Consequently, the entire reaction is pushed to a completion. It may be noted that the dissociation of oxenium ion, step second, requires the supply of energy. This is made available through the solvation of a reaction, considering energy being released by the step up of ion dipole bond between the carbocation and solvent molecule. Relative age of a dehydration of alcohol. It has been observed that the age of dehydration of different classes of alcohol follows the order tertiary, secondary, primary. To account for this observed order, let us consider the rate of determining step in the dehydration of alcohol. That is, the dissociation of a protonated alcohol to form carbocation. This step include transition state involved in it may be depicted as the positive charge, it may be noted, is originally on the oxygen but in the product it is on carbon. In the transition state in which the carbon and oxygen bond is beginning to break, the positive charge is partially on oxygen and partially on carbon. This means that the transition state has acquired some carbocation character. As such, the same factor such that dispersal of positive charge which increase the stability of carbocation would increase the stability of transition state, lead to that ion and low its activation energy. This means that the transition state lead to the formation of tertiary carbocation, which is the most stable ion, would be most stable and therefore has least activation energy. In other words, such a transition state and a carbocation generated by it would be formed more rapidly. Consequently, the dehydration of alcohol would take place more rapidly. The dehydration of secondary alcohol, which involves the formation of less stable secondary carbocation, would naturally take place less easily. Similarly, the dehydration of primary alcohol involving the least stable primary cation would be more difficult to take place. Thus, the relative age of dehydration of alcohol would follow the same order as that of age of formation of carbocation. Orientation of dehydration. Many alcohol give rise to mixture of isomeric alkene on dehydration. The ratio of the alkene formed in a particular reaction depend upon reaction condition. However, in generally it may be stated that dehydration of an alcohol forms the formation of more stable alkene. For example, secondary butyl alcohol in the presence of H3PO4 and Al2O3 at 283 temperature give 1-butene 2.14% less stable and 2-butene 75.9% more stable. Both the isomeric butene are obtained by the explosion of H positive ion from the same carbocation formed as intermediate as shown. Secondary butylium ion give 1 butene and 2 butene. This implies that the stability of carbocation cannot have any effect on the ratio of produced product obtained. It may be noted, however, that G product is more stable than the other since it may be more highly substituted. A similar situation exists in dehydration of 2-methyl-2-butanol with 15% of H2SO4 at reflux temperature. 2-methyl-2-butanol in the presence of 15% H2SO4 give 2-methyl-1-butene 13%, 2-methyl-2-butene 87%. Here again the most highly substituted product and therefore most stable product is formed in predominating quantities. To sum up, it may be stated that dehydration of alcohol favors the formation of more stable alkene. Rearrangement of carbocation and formation of unaccepted product during dehydration. It has been found that during the dehydration of alcohol, some of alkenes formed are not what one would normally accept. The position of double bond formed or sometime even of a carbocation skeleton may be quite unexpected. For example, the dehydration of N-butyl alcohol give a mixture of a 2-butene main product and 1-butene, whereas normal only 1-butene should be formed. The formation of unaccepted product as shown above can be explained in terms of rearrangement of intermediate carbocation. It has been observed that carbocation tends to rearrangement to form more stable ion. This rearrangement usually involves the migration of an hydride, such that hydrogen atom along with the pair of bonding electron form an adjacent carbon atom to the positively charged carbon of a carbocation. Such a migration is known as hydride shift. Alternatively, the rearrangement may occur through the migration of alkyl group, which it pair of a bonding electron from the adjacent carbon to a carbon having the positive charge. This type of migration is known as alkyl shift. Since such migration generally involve only adjacent carbon, they are also termed as 1,2 shift. Example of hydride shift. In the dehydration of an butyl alcohol, the intermediate carbocation initially formed. This undergoes a 1,2 hydride shift to form the more stable secondary butyl ion. This ion in turn loses H positive ion to form the more stable 2-butene as the preferred product. Example of alkyl shift. In the dehydration of 3,3-dimethyl-2-butanol, the carbocation initially formed is a secondary carbocation such that 3,3-dimethyl-2-butyl ion. This undergoes the immigration of methyl group with a bonding pair of electrons from an adjacent to the positive carbon to form the more stable tertiary carbocation, namely 2,3-dimethyl-2-butyl ion. The ion thus formed lost a hydrogen ion to form 2,3-dimethyl-2-butene as the main product, which is more stable than the expected product 3,3-dimethyl-1-butene. Partially dehydrated alcohol to form the mechanism of reaction as discussed later in section 6.3 reaction number 3. Second, oxidation of alcohol can be carried out with a variety of reagents such as aqueous acidified and alkane potassium permanganate, acidified sodium or potassium dichromate, dilute nitric acid and CrO3 in pyridine. The case of oxidation and the nature of product obtained depend on type of alcohol employed. First, primary alcohol are easily oxidized by potassium permanganate, acidified sodium or potassium dichromate or dilute HNO3 to aldehyde and then to carboxylic acid containing the same number of carbon atom as the original alcohol. For example, ethyl alcohol in the presence of oxygen give acid aldehyde then acetic acid. It is possible to arrest the reaction of aldehyde state by using a stable oxidizing agent such as acidified K2CR2O7 and distilled away the aldehyde as soon as it is formed. Some special oxidizing reagents have also been developed which oxidize primary alcohol to aldehyde state only. One such reagent is pyridine chlorochromate (PCC), formed by mixture chromic trioxide, pyridine and HCl. It is used in methyl chloride solvent, for example, N-butyl alcohol in the presence of PCCl and CH2Cl to give buta butyraldehyde. Secondary alcohol on oxidizing first give ketone with a same number of a carbon atom. Ketone are further oxidized only on dramatic treatment to give acid containing less number of a carbon atom. For example, isopropyl alcohol in the presence of oxygen give acetone, then acetic acid. Opnier alcohol oxidation. Secondary alcohol can also be oxidized by refluxing which acetone in the presence of aluminium isopropoxide or aluminium tert butoxide. The alcohol taken is oxidized to the corresponding ketone while ketone is reduced to isopropyl alcohol. Secondary alcohol plus acetone give in the presence of aluminium isopropoxide give ketone and isopropyl alcohol. This process is partially suitable for oxidation of unsaturated alcohol and is known as Opnier alcohol oxidation. Secondary. Third, tertiary alcohol fail to undergo oxidation in neutral or alkyl solution. However, which with acid oxidizing agent they are oxidized to give a ketone and acid containing less number of a carbon atom than the original alcohol. For example, tertiary butyl alcohol in the presence of oxygen give acetone plus carbon dioxide plus water. Third, action of heat reduce copper. Different classes of alcohol furnishing different product when their vapor are passed over reduce copper at high temperature 475 to 575 Kelvin. First, primary alcohol are dehydrogenated to form aldehyde. For example, ethyl alcohol in the presence of copper and 575 degree temperature give aldehyde plus hydrogen. Secondary alcohol are also dehydrogenated to give ketone. For example, isopropyl alcohol in the presence of copper at 575 degree Kelvin temperature give acetone. Tertiary alcohol are dehydrated to give alkenes. For example, tertiary butyl alcohol in the presence of copper at 575 degree Kelvin temperature gives isobutylene. Distinction between primary, secondary, and tertiary alcohol with Lucas test. The most convenient and common use method of distinguish between different classes of alcohol is the Lucas test. It consists in treating the alcohol and the Lucas reagent, which is an equimolar mixture of a concentrated HCl and aqueous ZnCl. 2. Appear of a cloudiness in the reaction mixture indicate the conversion of alcohol into alkyl chloride. It has been observed that first, tertiary alcohol react immediately and therefore cloudiness appear immediately. Second, a secondary alcohol react within about 5 minutes when the cloudiness appear. Third, a primary alcohol does not react appreciably at room temperature, therefore no cloudiness appear. An older method for distinguish between primary, secondary, and tertiary alcohol, known as a Victor-Mayer test, is seldom used these days. Dehydrated dihydric alcohol. Dihydric alcohol are compound containing two hydroxy group attached to a different carbon atom in their molecule. They are known as diol in UPSC system and glycol in common system. For example, ethane diol, ethylene glycol. Nomenclature. First, common name. The two hydroxy group in a glycol are used attached either to adjacent carbon atom called 1,2 or vicinal group or a carbon atom situated at the extreme end of a carbon chain called polymethylene glycol. In the common system, vicyline alcohol are named after the common name of corresponding alkenes, while polymethylene glycol are named according to the name of a methylene group CH2 present in the group as given below. Ethylene glycol, propylene 1,2-glycol, trimethylene glycol. Glycol which are neither vicyline nor polymethylene are also named after parent alkene by specifying the position of hydroxy group by suitable number. For example, butylene 1,3-glycol. Sometimes the position 1, 2, 1, 3, 1, 4, etc. are indicated by alpha, beta, and gamma, etc. For example, alpha propylene glycol, beta propylene glycol. Second, IUPAC name. In the IUPAC system, all dihydric alcohol are named as diol of a parent alkene. The position of OH group being indicated by suitable number as given below. First, the long straight chain of a carbon atom which must include the two carbon carrying the OH group is selected and the name of a corresponding hydrocarbon is written. Second, the chain is numbered from the end which gives the lowest position number to the carbon carrying the OH group. Third, the suffix diol is added to the name of a parent hydrocarbon along with the position of the OH group. Fourth, the name of a side chain and other substituent, if any, are prefixed before the name of the diol along with their position in alphabetic order. For example, ethane 1,2-diol, propane 1,2-diol, propane 1,3-diol, 2,3-dimethyl butane 2,3-diol, 1,2-diphenyl ethane 1,2-diol. Method of formation. The main method used for formation of glycol are given. Hydroxylate of alkenes. Glycol can be prepared conveniently by the hydroxylation of alkene by treating with potassium permanganate solution or oxonium terrat oxide. Give dihydric alcohol. For example, ethylene glycol is prepared by hydroxylate of ethylene as shown ahead. Ethylene in the presence of KMnO4 and water give ethylene glycol. The reaction is known as cis hydroxylate as it proceeds in a stereospecific manner lead to the formation of a cis diol. For example, cyclopentene give in the presence of KMnO4 and water give cis cyclopentene 1,2-diene. Second, hydrolysis of epoxide. Glycol can also be prepared by acidic catalyzed hydrolysis of epoxide which involves the cleavage of epoxide ring. For example, ethylene glycol is prepared by the hydrolysis of ethylene oxide as shown below. Ethylene oxide in the presence of water plus acid give ethylene glycol. Epoxide themselves are usually prepared by treating alkene with a pre-oxy acid. For example, ethene plus pre-formic acid give ethylene oxide plus carboxylic acid. It may be noted that hydrolysis of epoxide is also stereospecific and lead to formation of trans-diol. For example, cyclopentene oxide in the plus water in the presence of acid give trans cyclopentene 1,2-diol. Third, hydrolysis of a vicinal dihalide alkane. Diols can also be prepared by the hydrolysis of a dihaloalkanes. For example, ethylene glycol can be prepared by hydrolysis of dibromine ethane as shown below. Fourth, bimolecular reduction of carbonyl compound when treated with magnesium in an inert solvent such as benzene and ether under alkene condition. Aldehyde ketone undergoes bimolecular reduction to form vicinal glycol. For example, ketone in the presence of benzene and Mg and second water give biphenol. Fifth, reduction of dicarbonyl compound. Diol can also be prepared by reduction of a dicarbonyl compound just as monohydric alcohol can be prepared by reducing aldehyde and ketone. For example, butane 1,4-diol in the presence of hydrogen and nickel give butane 1,4-diol. Sixth, reaction of a diketone with Grignard reagent. This method can be used for the preparation of higher vicinal glycol. For example, butane 1,2-diol give in the presence of RMgX plus hydronium ion give 1,2-glycol. Physical properties. Physical state. Glycol are generally colorless, viscous liquid having a sweet taste. Second, higher melting point and boiling point. Glycol undergoes intermolecular hydrogen bonding to a greater extent than monohydric alcohol. This is because they contain two sites for hydrogen bonding per molecule. As a result of expensive hydrogen bonding, glycol has much higher melting and boiling point as compared to monohydric alcohol. For example, the boiling point of ethylene glycol is 470 Kelvin as compared to 351.5 Kelvin for ethylene alcohol. Solubility. Glycol has a greater solubility in water than the monohydric alcohol. This is again due to more extensive formation of hydrogen bonding between glycol and water than between monohydric alcohol and water. Chemical reaction. Like monohydric alcohol, glycol exhibits the usual reaction of hydroxyl group such as reaction with metal like sodium, reaction with halogen acid, acidification, etc. At the same time, glycol undergoes certain reactions that are typically one of a alcohol having two or more alcoholic groups. We will now illustrate the important reaction of glycol by taking vicinal group as a typical example. First, reaction with metal, acidic nature. Like monohydric alcohol, glycol react with metal like sodium to form mono and disodium derivative and liberate hydrogen. For example, ethylene glycol in the presence of sodium at 333 Kelvin temperature give monosodium glycolate, then disodium glycolate. It may be noted that two OH groups react one by one at the same time. The second OH group reacts slowly as compared with the first. This is because in the diol molecules, the electron attached to an inducive effect of one hydroxyl group make the hydroxy group more acidic in nature and it reacts with metal quite rapidly. But in the product formation in the first stage, the CH2O pair exert an electron releasing effect which decreases the acidic character of a second OH group. Second, reaction with halogen halide, it reacts with HCl and HBr to form two different products as shown below. Ethylene glycol plus HCl at 433 Kelvin temperature give ethylene chlorohydrin, then ethylene dichlorone. It may be noted that the first stage of reaction takes place more rapidly than second. This can be understood in terms of mechanism of reaction. The reaction involves the initial protonation of OH group to form oxygen ion, which then undergoes nucleophilic attack by halide ion to form a halo derivative. After the substitution of OH group by Cl, the electron density around the oxygen and of the second OH group decreases because of strong electron attracting inducing effect of chlorine. As a result, protonation of an electron second OH group does not take place easily. With HI, diiodine form decomposition to give alkene. For example, glycol in the presence of HI give CH2I, CH2I, then give ethene plus iodine. Reaction with PCl5 or thionate chloride. Glycol react with the phosphoric pentachloride or thionate chloride to form dichloride. For example, glycol plus PCl5 give dichloroethane plus POCl3 plus HCl. Glycol plus SOCl2 gives dichloroethane plus SO2 plus 2HCl. Reaction with phosphoric trihalide when treated with PCl3 or PBr3, glycol form dichloride or dibromide. However, with Pi3 diiodide first form being unstable, decomposed to give alkene and iodine. For example, glycol plus 2Pi3 give unstable dihalogen, yeah, dichloride. Then dichloride convert into ethene plus I2. Reaction with nitric acid. When heated with concentrated HNO3 in the presence of concentrated H2SO4, glycol form dinitrate. For example, di, uh, glycol plus HNO3 in the presence of H2SO4, ethylene dinitrate formed. 6. Dehydration. Dehydration of glycol under different conditions give different product. This is illustrated below by the condition. The example of ethylene glycol. First, when heated to nearly 775 Kelvin, ethylene glycol form ethylene oxide. Ethylene glycol heated up to 775 degree Kelvin form epoxide, ethylene oxide plus water. Second, when treated with zinc chloride Under pressure of in a sealed tube, ethylene glycol get dehydrated to form acetaldehyde, formed through arrangement of a vicinal alcohol. Ethylene glycol in the presence of anhydrogen give vicinal alcohol, unstable. Rearrangement acetaldehyde. Third, when distilled with concentrated H2SO4, glycol form dioxane as shown below. Fourth, on heating with concentrated H3PO4, ethylene glycol form diethylene glycol. Seventh, reaction with aldehyde and ketone. Glycol undergoes condensation with aldehyde and ketone in the presence of para-toluene sulfonic acid, commonly called PTS, to form cyclic acetal. For example, aldehyde plus glycol gives cyclic acetal. The compound formed by the reaction of ketone with glycol were earlier termed as cyclic ketones, but now the term cyclic acetal is used both in case of aldehyde and ketones. 8th, reaction with organic acid. Glycol react with organic acid to form mono or diether depending upon relative amount of glycol and acid. For example, glycol in the presence of organic acids give glycol monoacetate or glycol diacetate. Oxidation. Glycol give different product on oxidation under different condition. In generally, the oxidation may be depicted as follows by considering the example of ethylene glycol. Ethylene glycol when oxidated give glycol aldehyde. When then further oxidated give glycolic acid or glycoxal. Then further oxided give glycoxalic acid. Then further oxidizing give oxalic acid. When oxidizing with nitric acid, ethylene glycol ultimately give oxalic acid even though the intermediate product can be isolated. 10th, oxidative cleavage of 1,2-glycol. When treated with peroxide or lead tetraacetate, compound containing two OH group attached only adjacent carbon atom undergoes oxidation cleavage. The reaction break carbon-carbon bond and yield carbonyl compound as oxidation product that is given. It may be noted that for every carbon-carbon bond broken, an additional CO bond is formed as each carbon. It may also be noted that in this reaction, periodic acid is found to work well in aqueous solution, while lead tetraacetate give good result in organic solvent. The oxidation cleavage of 1,2-glycol with peroxidic acid is also known as a Melparade reaction. Mechanism of oxidation cleavage with peroxide acid. Peroxide acid. In aqueous solution, hydration of peroxide acid take place to form H5IO6 having the structure. This undergoes ionization to form an active species H4IO6 negative. That H4IO6 negative converts glycol into a 5-member cyclic ester first, which eliminates a molecule of water to form another 5-member cyclic intermediate second undergoes tumulus oxidation reduction with the cleavage of a carbon-carbon bond to form a product as shown ahead. Mechanism of oxidation cleavage with lead tetraacetate. Lead tetraacetate react with glycol to form a 5-member cyclic ester which get decomposed to form product as shown ahead. Utility of a reaction. The reaction usually takes place and quantitative yield and is very useful in a structure determining particular in the study of carbohydrate which are a polyhydroxide, aldehyde or ketone. It gives valuable information by determining the quantity of oxidizing agent used and the nature and the amount of product formed as illustrated below. A structure determine. Let us consider an oxidation cleavage of a 3 isomeric butadiol, 1,2-butanediol, 2,3-butanediol and 1,3-butanediol are periodic acid. First, 1,2-butadiol react with 1 mole of HiO4 to give a mixture of formaldehyde and propanaldehyde. Second, 2,3-butadiol also react with 1 mole of HiO4 to give acetaldehyde. Third, 1,3-butadiol does not react with HiO4 because it does not have the OH group attached to adjacent carbon atom. Thus, the study of a reaction with HiO4 can lead to the structure elucidation of a given diols. Determination of number of OH group on adjacent carbon. In case of polyhydric alcohol, the number of molecules of oxidizing agent used in the reaction also indicate the number of OH group present on adjacent carbon. For example, 1 mole of glycol reacts with 2 mole of HiO4. This establishes the presence of 3 OH group as adjacent carbon as shown below. C. To determine whether the OH group are present in vicinal position or not. Quantitatively, the occurrence of a reaction between polyhydric alcohol and HiO4 is established by the formation of white PPT of AgIO3 on adding AgNO3 solution to reaction mixture. If the PPT is formed, it means that the given polyhydric reaction alcoholic reaction with HiO4. Therefore, it have been OH group attached to the adjacent carbon. On the other hand, if no PPT is formed, it means that the given alcohol does not react with HiO4 and the OH group are not attached to adjacent carbon. Mechanism. A. Oxidation with periodic acid. Oxidation cleavage with periodic acid is believed to take place through a cyclic intermediate formed by the attack of a pre-oxidate ion on glycol as shown below. B. Oxidation with lead tetraacetate. This reaction is also believed to occur through a cyclic intermediate which undergoes an oxidation reduction process leading to a cleavage of a carbon-carbon bond. 11th, pinacoline reaction. It is the typical reaction of higher glycol involving formation of a rearrangement product. It was the first observed in case of pinacol such that 2,3-dimethyl 2,3-butadiol and hence the name of pinacol rearrangement. It was found that on treating with sulfuric acid, pinacol undergoes dehydration which with molecule rearrangement of form methyl tetrabutyl ketone, also known as pinacoline. That is, many other vinyl glycol are now known to undergo similar acidic catalyst reaction. All these reactions are therefore collectively known as pinacoline rearrangement mechanism. The pinacol rearrangement takes place through stepwise mechanism as depicted below. Step first involving protonation of a pinacol. Step second, the protonation species lose a molecule of water to form a carbocation. Step third, the carbocation undergoes rearrangement involving a 1-2 shift of electron deficient carbon to generate a new, more stable ion. This ion in turn eliminated a hydrogen ion to yield the final product. In some cases, the step involved removal of water and shift of alkyl group may take place simultaneously. Important observation. First, relatively stability of a carbocation. In case of glycol having different group attached to the 2-hydroxyl group, the OH group which get hydrolyzed in the one which would produce a more stable carbocation, for example given. Second, migratory attitude of a group. In case of glycol having different group attached to a 2-hydroxyl group, it is not quite easy to predict the migration attitude of a group 2. In general, phenol group migrate in the presence of a alkyl group and hydrogen migrated in the presence of a 2. Both these groups. The above reaction clearly shows that in order to predict the final product of a pinacol rearrangement, the relative stability of carbocation intermediate as well as relative